Hello everyone. So today we're going to talk about the non-escape of mass for the horocycle flow. So we already seen some of it. So what we want to show is the following. So the main theorem is that the horocycle flow orbit is either periodic. So here, of course, we are still in the unit tangent bundle mod gamma, where gamma is a lattice subgroup of PSL2R or SL2R if you want. And so we want to show that the orbit of the horocycle flow is either periodic, or if it is not periodic, then we can look at the average of any compactly supported function f, and then as t goes to infinity, it will go to the space average, but not just any space average, it will be the space average with respect to the Haar measure. So mx here is the Haar measure as before. And so to prove the theorem, we need to show that, so we first show that any limit, any sequential limit, so any limit of sequences at certain time stamps, so let's say Tn, so let's look at the time average of f, or actually the time average of the Dirac delta measure from 0 to Tn. So Dirac delta measure on what? On the horocycle flow orbit, right? So in terms of, if you start at x, it will be x u minus of negative t, dt from 0 to Tn. Okay, so this, so we're looking at the time average at any given sequence, Tn, and we want to show that this has total measure 1. When the total measure is 1, then we say that it is a probability measure, right? And so this is usually called quantitative non-divergence. Okay, so not only it is not divergent, but it is some sort of escape of it's non-escape of mass, in other words. So here mass means some part of the, so if the total measure is less than 1, then some part of it went somewhere, and that somewhere would be points at infinity, right? So here we're saying that there's no mass of escape, which is escaping to infinity. All right, so the non-divergence was first proven by Margulis in a much more general setting than now. So, but what does it mean? It means that for now, so X is the quotient space as before. So you can think of it as SL2R mod SL2Z or SL2R mod gamma. And for every X, there exists some complex subset of X such that, and sequence of times such that at those times, the horocycle orbit comes back to the compact part, okay, for all Tn. And so for X in X, so Ht of X is the horocycle is a horocycle. So unless it is based on ad infinity, if it is based on ad infinity in the upper half plane, it would look something like that, like a horizontal line. Or if it is not based on infinity point, then there will be some point on the real axis, which is the base point of the horocycle, right? So it will look something like this. And X is a vector pointing, let's say that it is not upward. So this is not the case. This is the case we're looking at. So by taking, well, what do we want to take for the compact set? So we want that to come back somewhere. So we're going to take the compact set to be all the vectors such that the base point, maybe I should write another x, let's say x prime, such that the base point of x prime has image part equals 1. Okay, so it's going to be all these. We have to cut by the fundamental domain, so I don't know where, but let's say that this is maybe part of my fundamental domain. Then I'm looking at all the vectors based on imaginary part, based on the line, horizontal line, y equals 1. Okay, so this is my compact part. And then what do we see? If we see that from the picture, we already see that here, when you start from any vector like that, or actually any vector like this. So the vector that we start with, this is my x. So you see that at some point you come back, right? So you see that h t1 x comes back for some t1. Okay, so now we're going to repeat this process with ht1 x. So replace x by ht1 acted on x. Then there will be some t2 such that ht2 ht1 x belongs to L, right? So you repeat this, and then you'll get some sequences going to infinity such that h of tn. So these are not the same, and t. So tn prime will be summation from t1 to tn. So, and we know that there's these sequences that the whole cycle orbit is coming back to the compact part. All right, so now let's talk about the quantitative non-divergence. So this version is due to Dani. So what does it say? It says that first part is that for any lattice subgroup of SL2R and any compact subgroup of X, any positive epsilon, there exists a compact set that depends on K and epsilon, such that, so what do we want? We want some quantitative version. So we want to look at the parts that is outside of the compact set. Okay, so the whole cycle orbit, HTX, does not belong to the compact set. Okay, so we want to look at the part that is not coming to the compact set, and we want to say that it is very small compared to T. Okay, so the whole time compared to the whole time T, the time that is outside a compact set, the given compact set is very small, epsilon. Proportion is only up to epsilon. And for every T and for every X, starting from the compact set given. Okay, so we cannot have the same statement here. So this statement is not possible to get if you don't start from a compact set. Okay, so be aware that we have to start from any given compact set. So fix any given compact set, and then we can find such compact set L. Okay. And then the second part is that, so we conclude that for every point, either X is periodic, or there exists some time such that star holds for every T bigger than T sub x. Okay, so if you don't start from a compact set, then you cannot have star, but you can have star from a sufficiently large time. So if you start from any vector, then you don't know that the whole cycle flow is most of the time in the compact part, right? It is almost trivial that you cannot do that, right? Because if you start from, say, very, very, very close to the cusp, then it stays, at least at some, up to some point, it stays in the cusp part, right? Anyway, so this is all you can say for generic point, for not for generic point, but for every point. For every point, either x is periodic. If it is not periodic, then it stays in the compact part most of the time, starting from large enough time. Okay, I hope the theorem is clear. So most of the time it stays in the compact part, but you need to be careful that it comes with this fact that it should be for large enough time. Okay, so let's say that it is most of the time stays in the compact part, starting at a large enough time. Okay, so the whole cycle. All right. So let's see. So now we worked with the geometry that is not really the geometry of the hyperbolic space, but really the geometry of x2. So we will work with the geometry of x2. Here we are looking at the space of lattices. Okay, space of unimodular lattices. So these are unimodular lattices in R2. Okay, so this geometry is coarser than the upper half plane. For when, oh, actually I should say, so caution. The space of unimodular lattices in Rn, so SLN R mod SLN Z, the topology is coarser than the Riemannian structure. Okay, so for example, it's just one point. It is equipped with, the topology is equipped with one-point compactification of the space, right? Why? Because of Mahler compactness criterion. Okay, so for the proof, so remember that by Mahler, Mahler compactness criterion, K must be, so K is a compact set, so it must be inside this omega sub D, which is the set of lattices, unimodular lattices, such that the ball, the delta ball, intersection with the delta ball is just the identity, right? So for example, if you look at the standard lattice, Z cross C, Z direct sum Z, so it looks like this, right? So if you look at small enough delta, then the delta ball around 0 will look like this. So the intersection is only just the point 0, right? So it means that there is no vector, no element of lambda that is inside the delta ball, all right? For some delta, this is my delta. Okay. So now, what do we want? So we want to choose eta between 0 and delta over 2. So we're taking purpose delta over 2, such that, so L will be omega eta. And we want the property that we want to show. So property star. So in other words, the orbit, the whole circle orbit that is not inside our choice of complex set L is, the proportion is only up to epsilon, at most epsilon. Okay, so has the property star for every lambda in K and every T positive. All right. So now, since we're using Mahler compactness criterion, we want to look at the vectors. And we only need to look at the primitive vectors that are not presentable, so not a linear combination of other vectors, right? So let's choose a maximal set of mutually independent primitive elements, right? So primitive means that it's not like, for example, constant times another, positive, say, integer times another vertex of another vector of the lattice. All right, so what do we know? We know that by Mahler compactness criterion, it is in L if and only if there exists some vector, would be just any vector, but could take it as a primitive vector such that u minus of t vi, the length is less than eta. If there's some vector for which the length is less than eta, I should say HTF, right? So now, since lambda is in so we chose lambda here, so it is in K, so it is in K, so it is in omega delta. We know that all the primitive vectors has length bigger than delta, okay? So now fix some t. Then for each I, we're going to look at the good times. So this is the time. So good is good for us. So the whole cycle orbit is in the, BI is the bad times. So it is when there is a vector of which is very small. So here we're looking at each vector. So we'll keep tracking of each vector vi. So if the whole cycle orbit u minus t vi is very small, so it's in the eta ball, we say that it is a bad time for vi, right? So this is bad times. Okay, and then pi will be time that is not inside the delta ball. Okay, so, and it's called the protected time. Again, for vi. Okay, so what do we know? We know that we have eta, which is smaller than delta. So we have delta, omega delta, and there is there's this k here. Maybe it has not so nice boundary. Okay, and there is this omega eta. So eta is smaller, so it is a smaller neighborhood of the cusp, right? So if your whole cycle flow is in this small neighborhood, so small neighborhood of the cusp, so this means that, so if this is true, then if your ut u minus t of vi is in the eta ball, then your lattice u minus t of lambda is not in the compact part, omega sub eta, right? Now, if your t is in the intersection of PIs, for every I, then, so all the vectors are all delta big, so it should be inside omega delta, right? So u minus t of lambda should be omega delta in the, say, compact part. So omega eta will be L, and omega delta is something between K and L. Omega delta. Okay. Now if I is not equal to J, then Pi intersection Pj is empty. Why is this true? So this is the specific. This is only true. Yeah, I should say only true. This is only true for SLN R minus SLN Z n equals 2, right? So why is this true? Why? Because in the in R2 we have two vectors that span the fundamental domain. For example, something like this. So let's say that you have such a lattice. Then you have this vector v1 and v2 that spans the quadrilateral, which is the fundamental domain for the lattice action in R2, on R2 by translations, right? And this fundamental domain is, since we're looking at the unimodular, space of unimodular lattices, it has area 1, right? So since it has area 1, if the vector v1 is very small, vector v2 cannot be small. So if the vector v1 has length less than 1, v1 is less than 1, then v2 should be bigger than 1. Otherwise, it's the area of the quadrilateral spanned by v1 and v2 cannot have b1, right? Whereas in dimension 3, if you look at the parallel pipe, so you can have two very small vector if the third vector, the last vector, is fairly large, right? So it's possible to have this area small, but the volume of the parallel pipe still 1, right? So can have two vectors of length less than 1, right? If you're looking at n-dimensional unimodular lattices in Rn, right? So in lattices of Rn. All right, so we're looking. So the conclusion is that Pi is intersection Pj is empty. Okay, so we're looking at the time such that u minus of t lambda is not inside L, not inside the compact part. And this is equal to the set of times such that u minus of t of vi is of length less than eta for some vi. So this is equal to union of all the bad times for vi's. And so it is less than, it happens that it is less than 4 eta over delta of MR of the disjoint union of PIs. So this is non-trivial, we have to show it. And then, so the union of PI is of course all at most, it's just the whole time, so it'll be capital T. Right, so here we have to show that, so note that BI, so if it is in BI, it's bad time, so it's out there. So it's the time that it is not PI, so PI complement. So yeah, I should set here just a union. And for each of them, we are using 2 stars. So maybe I should do this. So let me here. So for 2 star, we're using the fact that, so this part, the left-hand side is bounded above by the summation of MR BI. And we want to show this. So PI, yeah, complement, right? So, so it's in BI, so it's time that is not good. So it's, yeah, actually, it's times that are good. Okay. Somehow I'm a little confused here. So it seems that it should be, BI should be inside PI complement. But somehow the textbook says BI is in PI. So is this PI or PI complement? So let's look at the computation and then we'll correct ourselves. All right, so we want to show star star. So let's say the VI is alpha 1, alpha 2. Then U minus T of VI is alpha 1 plus T alpha 2 and alpha 2. So if alpha 2 is 0 or alpha 2 is bigger than delta over 2, then U minus T of VI, the length will be bigger than 1, so there's no bad time for VI. Okay. If BI is not empty, then the protected time would be some interval, and it must contain some time such that T2 prime is in BI. In other words, alpha 1 plus T alpha T, alpha 1 plus T2 prime 2 prime alpha 2 is less than eta. So then, by our choice of eta, so eta was less than delta over 2, so it is less than delta over 2. Okay, so the measure of the length of pi, which is t2 minus t1, it is bigger than t2 prime minus t1. Okay, so it will be less than, at least alpha 2 inverse of delta over 2, right? Because this is exactly the length of t2 prime of this equation here, right? On the other hand, mr of bi is less than equal to mr of, so the bad times, if it is a bad time, then it has alpha 1 plus t alpha 2 eta is less than, alpha 1 plus t alpha 2 is less than eta. All right, so, yeah, actually I already said that, but, so it at most 2 eta over alpha 2, right? So, right, I was confused. I was going ahead of myself. This comes from, so this inequality, so the range of alpha 2, t2 prime would be at 2 eta over alpha. So the length of bad time, bi, is bounded above by 4 eta. So we're dividing mr, looking at the mrb over mr of p. So it is 4 eta over delta of the length of pi, right? So this is my epsilon. This is my epsilon. Okay, so still strange. So, all right, so if we have so there should be, so we're looking at small vectors, right? So this is complements, I should say, so protected times. The complements are, yeah, I think we're okay now. So bi, sorry for the confusion, pi complements are disjoint because the complements are the ones where you have a small vector, and you cannot have two small vectors at the same time, right? And we know that if you're bad, so if you're here, then you're here, right? So let me write it down. So this part is, if vi, your ut of vi, u minus t of vi gets inside this part, then you'd have bad time pi complement. If you have this even in a smaller cusp neighborhood, then you would have bad time bi, right? So bi is in the complement of pi complement. It is in the complement of pi. Okay, this is much better. So now we have pi complements, and pi complements are disjoint, so altogether it is n plus t, right? So I think now it's better. All right, so if you have pi complement, so this should be complement. If you're in the complement, then so we are inside this big cusp neighborhood. So big cusp neighborhood. So if you go in the big cusp neighborhood and then comes back, there's some point that you go inside the smaller compact neighborhood. Yeah, so what is this? Oh yeah, because the bad time is not empty. Okay, so it's possible that you go to the the cusp neighborhood, but you come back almost immediately, so that it doesn't touch this smaller cusp neighborhood. But if bi is not equal to 0, not empty, then it says that it's going inside to the small cusp neighborhood and comes back. So at some point, you have to go to the small cusp neighborhood, which is T2 prime. Okay, so now everything's okay, right? All right, so let's move on. So we showed the theorem, part 1. Okay, so part 1 is proved. Okay, so for part 2, let's choose delta equals, what is k? K is, yeah. So for the given neighborhood, we choose omega of 1/2, and for epsilon, we choose epsilon over 2. And then there is this L, which is L of omega 1/2 and epsilon over 2 that we found in part A. So it's a compact set such that the time that is bad, so where the horoscopic orbit is not inside the compact set, is less than epsilon over 2 times t. So this is what we showed for every t bigger than 0 and every x inside k. So here it's omega of 1/2. All right, so now if x is in 2 is not periodic, then there is this t1 such that u minus of t1 is in V has norm in 1/2 1. So then u minus t1 of V or x is in K. Wait, so has norm bigger than, should be bigger, it's bigger than 1/2. So choose tx. So for every V in x, so in x is my lattice. So choose t sub x such that t1 is epsilon over 2 tx. Okay. So now star would hold for all t bigger than tx. Okay, so it is almost clearly follows from part A. All right, so sorry for the confusion in the middle. So this is complement here that are disjoint, complement of the protected times. So here it's protected times. It's also protected times. Okay. All right, so let me stop here. Thanks.